Good afternoon. Thank you very much for attending this Coloquio of the Instituto Balseiro. It's a pleasure to introduce Zdenka Kuncic from the University of Sídney. Sorry for delaying the starting of this talk. Zdenka is invited through the Programa Maldacena to visit our campus. We had a nice week working together. We expect to continue doing so. And we'd like to thank very much Programa Maldacena, especially all the people behind the scene working for making this trip a real possibility. So in honor to the time, thank you very much for coming.
Do I need this, or this is working now? Yeah, so you can take that. Okay, thank you very much, Pablo. Thank you very much, everyone, for coming here this afternoon and for your patience while we sort out the technical issues. So the title of my talk, Synthetic Intelligence, is really about drawing a distinction between what we currently have, which is artificial intelligence, and also the intelligence, and probably the only example of true intelligence that we have at the moment, which is the intelligence that at least some of us have in our brains. So the reason why I called this a synthetic intelligence is because I also want to draw a comparison to other synthetic things. So for example, synthetic diamonds, synthetic drugs, synthetic fibers. The point is all of these things, these synthetic materials, can be made and can be made out of a bunch of different materials to mimic the functionality of things that we have naturally occurring in nature. So think about synthetic drugs, for example. Synthetic drugs are made based on some particular biochemical compounds that we already know exist in nature, and we already have some idea of their functionality, and we'd like to be able to reproduce that functionality, and the way we do that is by making synthetic versions of those particular molecules. So what I'd like to explain to you today is to try, by analogy, to make intelligence the same way. Can we make some materials, something physical, something tangible, and demonstrate that it has some intelligence in the same way in which our brains are actually made up of materials, chemicals, molecules, which together, through their interactions, produce intelligence? Now, I'm a physicist, so I'm also going to argue for there being some fundamental physical processes that we can hopefully try to mimic when we synthesize materials to produce something that we can call intelligence. Now, of course, that's just a description of the word synthetic there in the context of synthetic intelligence. What about the word intelligence? So intelligence, obviously, we have some kind of conceptual understanding of it, but with the era of AI, there's been a lot of questioning around what that actually means. If we go to the dictionary definition of intelligence, it means the ability to acquire and also apply information. So we can kind of keep that at the back of our minds when we approach this idea and this challenge of, can we make synthetic intelligence through different types of materials that can then exhibit some functionality that we can identify with intelligence in the same way or a similar way in which we identify some kind of intelligence associated with AI. But in my talk, I'm actually going to draw a distinction between artificial intelligence and biological or natural intelligence. And then I'm going to kind of explain and argue how and where synthetic intelligence fits into that scheme. So the first part of my talk is really going to kind of give a high-level overview of artificial intelligence, and then I'm going to draw a contrast to the biological intelligence that we know about that comes from our brains. And then I'm going to talk very briefly about some of the research that we and others around the world are doing to try and make brain-like synthetic intelligence. Okay, so first of all, everyone is now thoroughly familiar with AI because we're living in this era of AI. Now, incidentally, I created this slide for another talk that I gave way back in 2018. And when I was preparing my talk today, I was like, oh, I need to update this slide. And then I thought, well, no, hang on. It's actually kind of insightful to look at what's put up there. And there's still a lot of the same questions being asked today. Is AI going to replace lawyers? Is AI going to replace radiologists? So while there's been a lot of advances in the last 7 years, some of these questions are still open questions. We're still not there yet, despite all the advances that have been made with AI. So how does AI work? Well, first of all, you need a lot of data. And not only do you need a lot of data, but that data has to be high quality data. So AI really needs to have large volumes of well-curated data. So even before it does anything, that data needs to be, put into a state that it can be fed into a so-called AI model. And that so-called AI model is based on algorithms. So algorithms are representations of mathematical models and mathematical instructions. And then those algorithms are typically made so that the instructions then perform some predictions or estimation, something like that, for a particular task. Now, this is important because prediction is something that our brains do really, really well. Some people go so far as arguing that our brains are actually prediction machines. And there are specific models, AI models, based entirely on that premise. So the fact that AI does predictions really, really well actually is part of the reason why, in some cases, they perform just as well, if not better, than humans in doing certain tasks. So, of course, AI has been used for a lot of different applications and is still used for a lot of different applications. It is very, very useful. And for the purposes of this talk, when I talk about AI, what I really mean are artificial neural networks, and that's kind of like the type of model that goes into the algorithms behind the AI models themselves. And look, this is just a small list of typical applications, but of course the elephant in the room is LLMs, large language models. So in the last 7 years, since I originally prepared a similar talk to this one, LLMs have come onto the scene. And in fact, many people just think AI is LLMs. But this is really a particular type of AI model. It's called a generative AI model. And what they do is something very, very specific. They predict what's known as the next token. So if you give a series of words, they're really, really good at predicting what the next word will be or the next set of words will be. So again, it comes back to prediction. Models that do really well at prediction actually seem unnervingly intelligent, like they really mimic human intelligence. And so that's why there's so much hype today, because these Gen AI models that are really, really good at next token prediction are doing something that, our human brains do really, really well. So AI models are these abstract models based on algorithms, and the algorithms are based on abstract mathematical constructs. The reason why they're called artificial neural networks is because the mathematical constructs are very loosely based on neural networks in the brain, to the point where they use the word artificial neuron and artificial synapse. And that's what this diagram represents. So all of the circles in this diagram represents an artificial neuron, and all of the lines that connect the dots represents an artificial synapse. But that is where the similarity ends. It's really just using terminology that comes from the brain. But there is no real direct analogy with how real neurons and synapses operate. So this is a very, very simple description, abstract representation of an artificial neural network. Typically, they would have a bunch of artificial neurons in a row like this that represents some input, so data comes into the input. And then at the other end, there are neurons that represent output neurons, so kind of the result comes out at the other end. That's where a prediction might be made, for example. And then in the middle, there are a bunch of layers, in this case 3, but there can be many, many more, that are called hidden layers. And as the data goes from input to the first hidden layer, to the second hidden layer, and so on and so forth, these artificial neurons and synapses perform some mathematical transformations on the data that's put into them. And so what comes out at the other end is a completely different representation of the input data that is tailored to the specific machine learning task that that particular AI model has been designed to do. So if we drill down a little bit further, so that was just a sort of a diagrammatic sketch of these artificial neurons and synapses. If we take that down a little bit further, we can now relate this to what's being done mathematically in these algorithms. So the input layer consists of some vectors, and vectors just contain numbers. So data, at the very beginning when data comes in, the first thing that happens is that the data gets converted into numbers. Even images, they all get converted into numbers, okay? So that's what this input vector represents. Numbers in all these artificial neurons, single numbers. And then the hidden layers get converted into what's known as a weight matrix. Again, just a huge matrix with numbers in there, okay? And then lastly, on the output, you have an output vector. Again, just numbers in that vector. So everything is just based on numbers, and there are mathematical functions that operate with the weight matrix and the vectors, vector matrix multiplications, that continuously convert those numbers. This just shows one weight matrix, but there can be many, many more depending on how many hidden layers there are. And speaking of many layers, this is the situation with some more complex AI models, such as the ones that are used in generative AI, and in particular for large language models. These are the transformer models. They have many, many, many layers of these multi-layer neural networks, and each layer has a slightly different architecture, a slightly different number of neurons, arrangement of neurons, and so forth, even some where neurons are not fully connected. So each of these layers is kind of like a separate model unto itself, and then they all interact mathematically in slightly different ways, and there can be a very, very large number of these layers. Now, this is the reason why we are hearing so much about these LLMs, is because they are quite sophisticated and complex models, mathematical models. But because there's so many of those layers and so many mathematical functions that need to be calculated over and over again, that they need all these GPUs in data centers to do that. Okay, so remember, each one of these layers has got multiple matrices in there, mathematical matrices that need to be continuously calculated. And when we say an AI model is trained, it means that each in each of these layers, all of those weights that connect the artificial neurons has to be optimized to specific values for the particular task. So for an LLM, the task is to predict the next token. So in each of those layers, the objective is to find the optimal value of those weights for the particular task. So that training process takes a long time, and GPUs are used to do that as effectively as possible. But then once that model is trained and people like us use it on our computers at the other end, we're doing what's known as inference. And inference is done on the trained model. Now, there are two interesting issues with the way in which this is done at the moment, this weight training paradigm. One is that it consumes a lot of power to train these models just because it's brute force optimization of those weights. So that obviously is just bang, 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 over and over and over again in the data center using GPUs until those optimal values are found. So that consumes a lot of power, takes a lot of time, so that consumes a lot of energy. Now, then once that model is trained, like a ChatGPT model, for example, and we start using it to perform inference, an individual instance of an inference is not particularly consuming a lot of power. It takes a relatively short amount of time, like a typical query might only take a few seconds, whatever, not consuming a particularly large amount of energy. But then you think about the millions and millions and millions of people who are doing this all the time. And that's what's stacking up in terms of the energy consumption problem that these transformer models now have. So this is a plot of computing performance in units of petaflops per day, going back from 1985 to this year, 2025, and this is published in a Nature article from a few years ago, so it's already outdated, but it shows you the trend of computing performance in the pre-GPU era. Yes, there was a pre-GPU era, which was sort of like around 2011, 2012, so you basically where you can see this break in the plot. And you can see that sudden change in the exponential computing performance going up there. And all of this is now just, GPU-based computing, all the way up to GPT-3, and now we have, GPT-4, GPT-5, and all the other ones that are now available through some of the other big tech companies. So this exponential trend is just continuing. And of course, associated with that is the energy consumption and the energy requirements to continue on that exponential trend. So this diagram shows the energy consumption globally between 2025 and 2035, and just in China and also just in the US. And you can see that the anticipated energy consumption, and this is just anticipated energy consumption for AI usage, is predicted to increase significantly in the next 10 years. But also the sources of the energy requirements are going to jump. And you can see here also there's an anticipated jump in nuclear energy production, both in China and the US. And I'm sure many of you have heard through social media and news and so forth that many of the big tech companies are planning to build their own nuclear power plants. So that just tells you something about, the actual physical requirements of this type of AI. And electricity is not the only resources that AI requires. There's also water to cool these data centers. And that's becoming almost as a significant problem as the electricity requirements on these data centers. So obviously this is unsustainable. So let's now move on to the brain, because the brain and the intelligence associated with the brain is at the other end of the spectrum. We're able to do what we do on minimal amounts of energy. And, you know, the sort of typical number that gets bandied around is that the brain consumes less than 20 watts of energy. But in addition to that, we're able to learn on the fly. We're able to adapt to information that is continuously being thrown at us. So how do we do that? You know, what are we missing between this, you know, the biological neural networks that our brains have and the artificial neural networks that are constructed mathematically and then algorithmically and then, you know, ultimately put in software that gets run on hardware in these massive data centers? There's this huge divide between the way in which AI is done now and the way in which our brains are working. So there's one thing to do with about the, you know, the power requirements, the energy consumption requirements, but there's also another major difference between AI models and artificial neural networks in particular and real biological neural networks, and that's depicted in this diagram here. This is a very nice and very recent diagram of what scientists think is the way in which the human brain is wired. And this is only a very, very small sample. I think it's something like 1 centimetre cubed or something like that. It's from the Allen Institute. It was just released earlier this year. This structure is completely different from the structure of AI models and transformer models in particular. So both the structure and the functionality of AI models is really, really quite different from that of the brain. Okay, so I just have to shift a little bit here because this is linked to a YouTube video that I'll play separately. Another really important point of distinction between AI models and real biological neural networks is that biological neural networks are adaptive. They're continuously changing in time. And so this is a nice little video that depicts this. Now, if I can draw your attention away from the Ibiza example down here, what I really wanted to highlight here is that it's not just, it's where the dynamics comes from. Everything's in motion. And there's two important processes here. One is physical, electrical signals, and the other one is chemical. You have all these ions and atoms that are moving around. So there are physical processes that underlie the way in which synapses and neurons and neural networks as a whole operate. So now we can ask the question, can we make physical systems that somehow mimic these physical and chemical processes in a device, in a hardware device? Okay, so this is the question that I'm proposing and presenting, that yes, of course, we can at least try to do that. Now that we have some insight, thanks to neuroscience, of what's actually going on in the brain. Even though we don't yet really understand how intelligence comes out of the brain, we can actually see the brain as a real physical system. and it's a dynamical system. AI models are not dynamical. Once they're trained, that's it, they're fixed into that state, and they just do really, really well at the job that they're designed and trained to do. If you tried to use an LLM model, ChatGPT or something, to do something else, it would fail because it's not designed to do that. So this adaptability and flexibility is a really important aspect of the brain's neural network, and it's a really important challenge as well to see if we can try and emulate that functionality in addition to emulating the brain's structure. I'll also point out that the very first AI was actually a hardware machine. It was called the Mark I perceptron, and it was built by an American engineer called Frank Rosenblatt in the 1950s. This was about 10 years after Alan Turing proposed his idea about, is it possible to build thinking machines? And Frank Rosenblatt developed this perceptron model using physical wires. And this is it. And this is him attempting to wire the whole thing and program the whole thing. Now, of course, back then, this is before the era of transistors. And so this is actually a massive thing. It took up a lot of space. People were still using vacuum tubes to try and compute things back then. So it took up a lot of physical space. Didn't work very well. And then, of course, about 10 years later, that's when transistors were invented and started to be developed, and people were starting to replace vacuum tubes with transistors. Transistors enabled everything to be miniaturized. So all of that, down to a very, very small scale. And transistors then also enabled logic circuits. And logic circuits then enabled algorithms to be invented based on, logic, Boolean logic. And so that's how we got digital computing as we know it today, logic-based computing. Now, incidentally, going back to Alan Turing, his famous Turing machine is actually a model for today's modern digital computer. But he also proposed another type of computing model. Actually, he proposed a few types of computing models. Another type of computing model he proposed was one based on a disordered system similar to the neural networks in our brains. And I don't know for sure, but I think Frank Rosenblatt got an inspiration from that Turing model for his Mark I perceptron. So, some of us are attempting to make neural networks physically in hardware as opposed to software. Why are we doing this? Because we already know that these AI software models are too complex. There's just too much overhead associated with them, and that's why we have these problems that we have at the moment with their electricity consumption, with the power requirements, with the water resource requirements of the data centres. So the way in which these AI models are used is problematic. So many of us, including the group here of Pablo and others, many other people around the world, are really attempting to find a different way to achieve devices that exhibit some kind of useful intelligence, that operate differently from AI. They're never going to replace AI. I think AI definitely is important, but there are definitely some limitations to AI, and there are definitely some opportunities where we can make different devices that operate more efficiently. So this is just one example. But we use nanotechnology in all our efforts, and the reason being we can actually pack a lot into a very, very small space on the same principles that Frank Rosenblatt's Mark I perceptron got miniaturized by transistors. So this is now going down yet another level using nanotechnology. So this is an example of a brain-like or neuromorphic architecture. And this is typically maybe tens of microns in width, made of nanowires. These nanowires are kind of long, maybe like a few hundred to a few hundred microns in length, but they're very, very thin. So maybe only like 10 nanometers thin. That's about 1,000 times thinner than the human hair. So, and you can see that they create kind of like this jumbled mess, kind of similar to the Mark I perceptron, the original one that I showed you, but obviously now shrunk down by many, many orders of magnitude in scale. We can make these kind of, hardware neuromorphic nanowires and put them on a chip, and then use that chip to deliver input signals and measure output signals, and try and manipulate them a little bit to see if we can apply some interesting machine learning tasks to demonstrate this physical nature of intelligence, or at least test that hypothesis that there are some physical processes that can produce what we would describe as being intelligence. So, some of the things that we've demonstrated so far using these devices, and again, there are other groups around the world that are making similar neuromorphic devices that use less power and sometimes less energy as well. Some of the examples of machine learning tasks that we applied include image classification and also sequence memory. So, for example, a sequence of numbers to be memorized, like a telephone number. Speech recognition, similar to what Alexa does, for example. Autonomous forecasting, in this case of chaotic time series. This is the famous Lorentz 63, butterfly chaotic attractor. Working memory. Working memory is something that our brains exhibit. It's the idea that you can focus on a particular task while also receiving information, different information, and processing that information without distracting you from the information that you're focusing on, the task that you're focusing on. To my knowledge, this has never been demonstrated by any AI model. And one of the other most exciting applications that we're currently working on is for space applications. Now, we currently have very many satellites orbiting Earth, taking photos of Earth all the time. Earth observation, there's a lot of data being generated from Earth observation satellites. And currently, a lot of people are also trying to apply AI models to analyse Earth observation data. Now, the way in which this is done at the moment is that the data that's generated on satellites is then transmitted back down to Earth. This is extremely challenging because that process is bandwidth limited. You also have to wait for the satellite to pass a ground station to transmit that data. And then, in order to apply AI models to that data, you need to train AI models in the cloud and then test it with the data. Now, what typically happens is that those AI models that are developed specifically to do some analysis of Earth observation data, that they're trained on data from that's available at the moment from previous sensors on board previous space missions. But then when those models get uploaded onto the satellites today, the sensors are completely different. And so the AI models actually don't work. So there's a really interesting challenge here. How can we process the data on board a satellite as it's orbiting Earth? Can we actually get some really useful intelligence by processing data on board a satellite? And so we've actually now developing a way we can do this using this neuromorphic nanotechnology idea, and therefore demonstrating that you can do this also on board a satellite without training any AI models whatsoever. This is really, really exciting because the other problem with this particular example is that Satellites are very, very resource constrained. They have limited power, they have limited memory, everything's battery operated, they have solar panels, you know, to get their energy sources. And so it's a very, very resource constrained environment. You don't have a data center handy to, you know, plug away at your AI model. And there are other similar examples of applications that are resource constrained where we think that this new way of developing, you know, intelligence and analysing data can be useful and makes more sense than using some of these existing AI models. So in the future also, of course, we're moving beyond Earth's orbit. There are a lot of projects at the moment that are headed towards the Moon, and Mars even as well. And there the need for intelligence and, you know, local intelligence on a device is even more pertinent. You know, it's impractical, impossible to send data back to Earth to operate in a data center to develop an AI model. So we actually need to have intelligence that is sitting locally on a machine like a robot, and that can actually process the data as it's being acquired, and that can spit out some, you know, meaningful predictions, some meaningful analysis for humans. And that's the end of my talk. Thank you very much for listening.
So, Zdenka, thank you very much. We have time for questions, comments, everything.
Thank you, Zdenka, for this very interesting talk. I'm very curious because I'm not in this field. What is the basic mechanism behind these neuromorphic structures, and what are they made of?
Yes, so in our case, the basic mechanism is to do with electron transport and also ion transport, so electroionic. So they are based on electrical junctions known as memristors or resistors with memory. So if you can imagine, everywhere where those wires overlap, there's a nanoscale electrical junction. And when the whole network receives an electrical signal, all of those millions, typically millions of electrical nanoscale junctions there will trigger the migration of ions initially, and then the ions neutralize and create atomic migration. And then there's also electron tunneling that triggers initially electrons moving across, and then eventually more electrons will move across. So it's electroionic. And that draws interesting parallels with the way that real biological neural networks work, because we know that they are electrically stimulated, and that also triggers neurotransmitter molecules to migrate from one synapse to the other as well. So some interesting parallels there.
Other questions, comments?
Hi, thank you very much for your talk. I wanted to know, do you have any more detail about the experiments you carried where you actually programmed these neuromorphic chips to carry out artificial intelligence algorithms?
Yes, thank you, yes. So we have about 2 or 3 different ways in which we can use these neuromorphic chips, these neuromorphic nanowire networks, to perform some machine learning tasks. One way is a way called reservoir computing, where you don't actually program or train the network at all. You just let it evolve in response to whatever input signals it receives, and then you read out from it. And from the readouts, you can then perform a simple machine learning task in one single layer. So if you think about a multi-layer neural network, the output layer is the layer that performs the final task based on all the data that's been pre-processed before it. So we just have one layer that can be attached onto the neuromorphic network. Another way to look at it is if you think about replacing all the hidden layers of an artificial neural network with just this one, physical hardware neural network, and then you can perform classification or prediction just using that one output layer. The benefit of doing that is because it's orders of magnitude more efficient. As a general rule of thumb, whenever you replace a piece of software with an equivalent piece of hardware that can do the same function, you gain efficiency. There are a couple of other ways we've also used these devices to perform machine learning and some kind of demonstrate intelligence. So for example, when I mentioned that working memory function, we use the network in a different way. There we actually developed some electrodes that fed signals, electrical signals, voltage signals into the network. And we also were able to train conductance paths in the network and associate those conductance paths with unique patterns from the input signals. And this is more like an associative learning device. So specific patterns can be are associated by the system by these unique conductance paths that form, and that can be trained in the network. And then the last example, which was for the space example, that one is the most exciting one because we did something very, very minimal there. We used the network just to generate feature vectors. So feature vectors are the things that come out neural networks. And then we used those feature vectors and we just performed a very simple algebraic calculation on them to do a specific task. In that case, it was to detect changes into different Earth observation images. So we've demonstrated a few different ways in which you can use these types of neuromorphic networks to perform useful tasks. Yeah.
Thank you very much.
Okay.
Thank you. I wonder, have you seen clustering or some kind of regions within the network, the neural network, depending on the task or with the nature of the input? I mean, different sources, sensitive motors, or something like that, like in brain,
Yes, so if I understand you correctly, the idea that there can be different modules, different regions of the network that might actually
or respond.
Yeah, respond to specific tasks that need to be done. So for example, it might be something like a vision task, maybe that gets done by some specific task. So we are aware of that in the brain, but it's not something that we're actively trying to emulate in these networks. However, what we have done is in simulation, we've actually shown that if you simulate networks with modular structure, and you get each of those modules to perform two different tasks, that the best performance is when those modules are not completely separate, that they have some connectivity there. And we think the reason for that is because then one module can kind of borrow some resources from the other module and vice versa. So those two tasks can be performed optimally together by that kind of modular but still connected structure. Yeah.
No, because I remember you mentioned yesterday, I think, about simple tasks and more complex ones.
Yes, so that was a sort of a different test that we did, yeah, so it was a little bit different, yeah.
Okay, thank you.
Other question?
Thanks for the very nice talk. My question is related to the physical process. So you mentioned that these membristors, I heard Eduardo's talks many times and also Pablo. Yeah. So there are processes like ions moving or filaments that form in between the wires and so on. So my question is related to the time, because you mentioned about, like, for example, preparing a chip and sending it somewhere.
Yeah.
But the question is, how are you sure that these processes are not like ions move back to diffuse to the original position, that change with temperature, humidity, everything? So how do you deal with the time problem? So how long it lasts, the training?
Yes, so I think actually there's two separate things there. So first of all, because for many of these applications we don't train the network, okay, so when we have a model, it's trained externally. So there's a very simple software model that gets trained, okay? We're just using the network to process the data. But the timescales in the network itself, you're absolutely right. These very important considerations to know how things are changing, how long they remain in certain states, and how to match that with the data that's coming in. So for example, you can change the sampling rate of data that's coming in, and maybe it stops working because it's just, there's a mismatch between the internal dynamics, or the dynamical timescales, and the timescale of the sampling rate of the data that you're putting in. So those are definitely practical considerations, very much work in progress, not just by myself, but everyone who's working in this field, yeah.
Thank you for your talk. It was really interesting. But concerning the learning of the network, the idea will be to have a mechanism to previously know the weights of the network and then to have it physically, or to have some kind of Hessian learning in the neuromorphic circuit? Or
yes, so definitely the latter. So, you know, I guess the paradigm that we're aiming towards is quite different from the weight training paradigm that current AI models use. So we're really trying to see if there's a fundamentally different way of getting intelligence other than the weight training paradigm. So in most of the applications, what we've done is just allow the network weights to evolve. We don't control them, we let them evolve naturally in response to the changing input signals. So in that sense, it's much more like Hebbian learning. The weights themselves are based on these memristors, which are adaptive, they're evolving all the time. And so there is also this idea and this analogy with synaptic plasticity operating in the networks.
Another?
I wanted to know about the comparison of the energy usage, since you mentioned that for AI. But before this, I wanted to ask you about the water usage for AI models, because I understand the water is recycled, most of it. So it's not an absolute use of water.
Yeah.
But it's sort of, it's not of so much concern as the other aspect, which is the energy. And how can you compare then the energy used here with the other models, with the other systems?
Yeah, so that is a very good point. First of all, the water issue, you're absolutely right, they are using recycled water. But, you know, all the Middle Eastern states are now starting to build their data centres. So where are they getting their water from? You know, so there are certainly, this is certainly more of an issue in some places than there are with others. Secondly, on the energy consumption, so the energy consumption comes from the fact that GPUs consume very high power, and that AI models take a long time to train, and that there are a lot of inference tasks going on. So that's where the energy consumption comes from. So to train these models is like orders of magnitude smaller. I mean, we can't draw a direct comparison without creating our own LLM model and doing a, you know, one-to-one mapping. But it's just like, it's chalk and cheese, because it's just such a fundamentally different way of doing things. So I don't have the hard numbers, but it is, you know, really, really fundamentally different, to the extent that you can't really benchmark against some of these AI models because it's just so different. Yeah.
I have a question. So far, you spoke and we work with synapses. What about neurons? What about?
Yeah, so I have a particular personal view on this. So if I may take a step back in answering this. So I mentioned early on there's a big research field known as neuromorphic computing, and as the title suggests, it's really taking inspiration from the brain to do computational intelligence type of tasks from these brain-inspired approaches. Now, sort of at the most basic level, the common denominator in all of these approaches is this idea of integrating both processing and memory, because at the moment, all our CPU chips, all the GPUs and so on, do processing and memory separate in this so-called von Neumann style architecture that was developed in the middle of the 20th century, and that's very, very inefficient. So by simply integrating processing and memory together, you immediately get efficiency gains. And indeed, that's how our brain does it. We just have neurons and synapses and memory and processing all over, distributed all throughout our brain. But that's where the commonality ends, because there are several different branches within the neuromorphic computing research community, and one of the biggest branches is the approach that tries to emulate what are known as point neuron models. So a single neuron, and single neurons exhibit a very specific action potential response to a voltage signal. And so these point neuron models are mathematical models for an individual neuron. And some neuromorphic approaches try to emulate that with an electrical circuit. So there are electrical circuits that emulate a point neuron model. My own personal view is that there is no such thing as a single neuron. Okay? How our brains work is through the network of neurons and their interactions.
Thank you.
Yes, neuroscientists can isolate individual neurons, but that's not how things work, in my opinion.
Okay. Question, comments? Zdenka will be another whole week with us working. So if any of you would like to meet her or discuss, welcome. You have to say that, but okay. I welcome you. Thank you very much again, Zdenka. Thank you
Pablo.
For the Programa Maldacena, and good afternoon.
Thank you.